Hello everybody. This video is provided to you as an opportunity to review example problem 5 from lecture 10, looking at plate and frame heat exchangers. For this problem, we are looking at slide 21 in lecture 16. Excuse me, it is lecture 16, not 10. We've done a lot. Where we have a plate and frame heat exchanger is being proposed to produce chilled water from an air conditioning unit. In this unit, 4,000 gallons per minute of water is cooled from 60 degrees to 44 degrees using an equal flow of water entering the exchanger at 41 degrees. If the plate spacing is approximately 33 millimeters, and the nominal water velocity on both sides is 0.5 meters per second. What is the overall heat transfer coefficient of the exchanger, the pressure drop, and how many plates are needed for this exchanger if the plates are approximately 4 meters high or long by 1 meter wide? So let's take a look at this, working it piece by piece. So for this problem, I've got a volumetric flow rate of 4,000 gallons per minute, which for the sake of this problem, I'm going to work everything out in metric units. So this comes out to be about 2.52 cubic meters per second. My mean velocity in each plate is approximately 0.5 meters per second. The density of my fluid, being water, is 1,000 kilograms per cubic meter. My viscosity is 1.31 centipoise, or 1.31 times 10 to the minus 3 Pascal seconds, or kilograms per meter second. The thermal conductivity of this would be approximately 0.576 watts per meter Kelvin. The heat capacity is 4184 joules per kilogram Kelvin. And the effective diameter that I'll use is going to be twice the spacing provided, which I said, I believe it was 3 millimeters. So the effective diameter is going to be 6 millimeters, or 6 times 10 to the minus 3 meters. So let's look at part A, finding U, or our overall heat transfer coefficient. So for this, I'm going to assume that U is equal to 1 over HI plus 1 over HO. And I'm also going to assume that HI is about HO, because these are both essentially water flows in the same dimensions, about the same velocities. So I'm going to make the approximation that I only have to solve for one heat transfer coefficient. Since it's a plate and frame heat exchanger, I'm going to be looking at the plate and frame expression that states that Nusselt, which is equal to H times the effective diameter over K, is equal to 0.37 times Reynolds to the 0.67 times Prandtl to the 0.33. So we need to find our Reynolds number and our Prandtl number. Reynolds here going to be calculated as density, velocity, effective diameter over viscosity. So I have 1,000 kilograms per cubic meter times 0.5 meters per second times 6 times 10 to the minus 6 meters divided by 1.31 times 10 to the minus 3 Pascal seconds. This calculation comes out to be 2,290. The Prandtl number can be calculated by the heat capacity times the viscosity over the thermal conductivity. So I have 4,184 joules per kilogram Kelvin times 1.31 times 10 to the minus 3 Pascal seconds divided by 0.576 watts per meter Kelvin. And I get a Prandtl number of approximately 9.52. With this, I can now calculate our Nusselt as 0.37 times 2,290 to the 0.67 times 9.52 to the 0.33, which is equal to 139. With a Nusselt, I can now calculate the heat transfer coefficient as 139 around Nusselt times our thermal conductivity of 0.576 watts per meter Kelvin divided by the effective diameter of 6 times 10 to the minus 3 meters. And I get a value of approximately 13,334 watts per meter squared Kelvin. With this, I can now find our overall heat transfer coefficient as simply 2 over 1,334 watts per meter squared Kelvin to the inverse, or is essentially half that. So my overall heat transfer coefficient is approximately 6,700 watts per meter squared Kelvin. The second part of the problem asks to identify our pressure drop. Well, assuming this is turbulent flow, because we have corrugated steel plates, we can calculate our pressure drop as 2 times their friction factor times density times velocity squared times length divided by the effective diameter, where F is equal to 2.5 times Reynolds to the negative 0.3. So for this, we have F equal to 2.5 times 2,290 to the negative 0.3 power, or our friction factor is 0.245. With this, I can then directly solve for our pressure drop in pascals or kilopascals as 2 times 0.245 times 1,000 kilograms per cubic meter times 0.5 meters per second squared times our length, which is 4 meters, divided by our effective diameter of 6 times 10 to the minus 3 meters. So if we do this calculation, we should get approximately 81.7 kilopascals as our pressure drop. The last part of the problem asks to identify the number of plates needed in this exchanger. To find that out, we have to compare the total flow rate in this system versus the flow rate in a single channel. So earlier I identified the total mass flow rate of this cooling water was approximately 0.252 cubic meters per second. Now the plate spacing was about 3 times 10 to the minus 3 meters. And that means that our basically our thickness or for flow for a channel or a channel width is probably going to be about half that, which means that our channel width is about 1.5 times 10 to the minus 3 meters. And if that thickness is essentially 1.5 millimeters and our width is 1 meter, we can essentially solve for our flow area No, hold on. Let me back up. The thickness is right. We have our velocity of 0.5 meters per second and our width of 1 meter. So our volume for channel is going to be essentially this 3 times 10 to the minus 3 meters times our velocity 0.5 meters per second times our width, which is 1 meter. There we go. And this isn't mass flow rate, this is volumetric flow rates. So I apologize for that. So what does this give us? This gives us about 1.5 times 10 to the minus 3 cubic meters per second of flow per channel. So the number of channels for this side is simply our 0.252 cubic meters per second divided by our flow per channel, or 1.5 times 10 to the minus third cubic meters per second, which should give us about 168 channels. Now this is for one side of the exchanger. To get the total number of channels, we multiply that by 2. Because we have a hot fluid and a cold fluid. And so it's 168 times 2, which is approximately 336 channels. And so we need to find the number of plates. It's simply the number of channels plus 1. So we need approximately 337 plates in this plate and frame exchanger. And that's how you work out this problem. If you have any questions, feel free to reach out to me via email. If not, thanks for watching.